Okay, continuing on, the nickel cadmium or NiCad cell is a voltaic cell consisting of an anode of cadmium and a cathode of hydrated nickel oxide, which is more or less this. It's not really on its own this kind of molecule. It's a little bit more complex, but that's a good form of it to show. Hydrated nickel oxide on nickel with an electrolyte of potassium hydroxide. So this is a common storage battery. The half cell reactions: cadmium plus OH minus goes to cadmium hydroxide and 2 electrons. And then this hydrated nickel oxide with water plus electrons goes to nickel 2 hydroxide. These half reactions are reversed when the cell is recharged. You can see both are very simple reactions, so that allows them to be reversed without too much trouble. The big thing about the NiCad batteries is that they can be recharged and discharged many, many times. Not too much more to be said about that, but just to indicate, you can see NiCad batteries all the time. This is what's going on within. They're being replaced by nickel metal hydride batteries, and you might see this abbreviation in your batteries for cell phones and other electronic devices. That's what you mostly see, and lithium ion batteries as well. They're replacing NiCad batteries, and the reason they're using them, cadmium is extremely toxic, so getting rid of the cadmium is always a bonus. These can be recharged many times. The lithium-ion batteries use a carbon anode and a lithium cobalt dioxide or lithium manganese compound as the cathode. They are light in weight and, again, can be recharged many, many times over the course of weeks, months, and years. So not too much more about that there, just those basic facts. Fuel cell, there are lots of different fuel cells. We'll focus on one here, but a fuel cell is a battery that operates with a continuous supply of reactants. That's what makes it different than the other batteries, is that the other batteries have their complete reactants within them, and that's it. Or say like the car batteries, we replace some of the water occasionally, but this is just a steady, continuous supply of the reactants. In the fuel cell that we're going to talk about that involves hydrogen and oxygen, we use a proton exchange membrane, the proton being H+, or PEM here for proton exchange membrane. And here are the half reactions. The hydrogen breaks up into H+ and electrons. Oxygen forms with H+ and electrons to form water. And so overall, it's just hydrogen and oxygen reacting to form water. Now, when we burn oxygen and hydrogen, it's a very exothermic reaction. But in fuel cells, we take those combustion reactions and we slow them down. We force them, the electrons, to go through a circuit, do some work for us, and we can really control this, what would otherwise be a very violent reaction. So what happens in here, we bring in hydrogen through into the, so this is a side angle of this thing. It's really, if you looked at it, if you saw a fuel cell, they look like just a big clump, like maybe 3 decks of cards strapped together. That's about the size of them, and the dimensions of them. So the hydrogen comes through. The platinum catalyst here allows the hydrogen to break up into H+ and electrons. The electrons, I didn't do a great job here, but the electrons are sent up and out to do work, whatever we want them to do. And then they make their way back here. The H+ now is small enough to make its way through the platinum catalyst with ease, and then through the proton exchange membrane with ease. And the oxygen can't make its way the other way. It's just too large. So it makes the H+ makes its way all the way over. It then reattaches with the oxygen and the electrons that are streaming in to form water. And if you hold up a fuel cell when it's working, it looks like it's broken because it's leaking. Water is leaking out of the fuel cell. But the nice thing about it is, I mean, that's what it's supposed to do. The other nice thing is that the only product is pure, ultra pure water. Now there are other types of fuel cells, just to mention a couple here. Methanol and hydrocarbons are used. So anything that can burn, anything that can react with oxygen can be used in a fuel cell. And we take it from being a combustion reaction that involves flames and heat and light, and we just change it in, slow it down, and force all of that energy to go into, or most of it, into electrical work. Okay, now the rusting of iron, this isn't a battery, but just to show you what happens when iron rusts. And we'll consider a piece of iron with a drop of water on it. What happens at the edges here, where the oxygen can come in from the air, that is where you get oxygen reacts with the water to form electrons, with electrons to form OH minus. The electrons come from the iron that is oxidizing, so it's changing into iron plus 2. The electrons are sent down here, and that provides the electrons for this reaction, because this isn't oxygen and water on their own aren't going to do anything, but here you're providing some the electrons, and the iron itself provides the pathway because it's low resistance, electrical resistance. So the iron is changing to iron plus 2. Electrons are shifted down here. Here we have the reduction, oxidation, and then OH minus that's produced in this reaction then meets up with the iron 2 that has been turned into become aqueous. They form together into the iron 2 hydroxide, and then that quickly oxidizes with oxygen to rust. So the important thing here is that the rust doesn't occur immediately. It forms first into iron 2 oxide, and then the iron 2 oxide, or hydroxide, I'm sorry, becomes our iron 3 oxide. So it's a two-step process. So the metal acts as the circuit, and let's see, and the iron has to make its way out to the outside of the to the center of the out from the center of the drop to meet up with the hydroxide ions that are being formed on the edge of the drop. So that's what's occurring when iron rusts. And to prevent that, like in a buried steel pipe, so you have this underground pipe that contains iron. If you want to prevent the iron from rusting, where there's lots of oxygen, lots of water for the rusting to occur. Well, you got oxygen and water and electrons. They form OH minus, just like they did in the drop, the water droplet. But and then you have iron that wants to oxidize, and I put in its potential. But then you have the magnesium. If you put a magnesium pipe or rod into the ground, and you connect it to the pipe, so you have something that is electrically conducting, the magnesium has a much larger positive potential. It doesn't matter what this potential is. You can make it whatever you want, whatever it turns out to be. It's just going to be added to this, or it's going to be added to this. So since they're both positive, whatever this number is, whether it's positive or negative, doesn't matter. Adding it to this will be a more positive or more spontaneous reaction by quite a bit, by almost 2 volts. So the magnesium, which is stable, we can't use sodium. We could use sodium here, but sodium wouldn't last very long in the ground. Magnesium is stable in the ground. Or I should say, it's going to react, but it's not going to react violently. It's going to react slowly, it's going to oxidize, and keep in preference to the iron. Now, the longer the underground pipe, the more magnesium rods you'll need. You can't connect this to a mile-long pipe and expect it to do all that work. And the magnesium will be eaten up. It's going to dissolve away, and eventually you'll be able to just take the post, if it's sticking out, and just pull the remains out, and then you know that it's time to replace the magnesium. And this process is known as cathodic protection. Okay, and I think that's it.